Welcome to this specialized module on information systems operations, focusing on the critical discipline of database management. In the modern enterprise, data is often the most valuable asset, and the database management system, or DBMS, is the vault that protects it. Today we will move beyond simple spreadsheets to understand how organizations structure, secure, and optimize massive amounts of data using sophisticated models and controls. We will explore everything from the rigid structures of the past to the flexible objects of the future, ensuring you have the knowledge to audit and govern these systems effectively. Let's start with the basics. What exactly is a DBMS? It is the software layer that sits between the end user or application and the raw data. Before DBMS, files were often duplicated across different departments. HR had a list of employees, and payroll had a separate list. This led to data redundancy and inconsistency. The DBMS solves this by centralizing the data. A critical concept here is the data dictionary. Think of it as data about data, or metadata. It contains the definitions of every field, who owns it, and how it relates to other data. If you lose the data dictionary, you might have the raw data, but you won't know what it means. We also distinguish between DDL, which builds the tables, and DML, which modifies the rows inside them. As auditors, we love the control a DBMS provides, but we must respect the risk. If this central system goes down, the entire operation stops. This diagram illustrates the protective role of the DBMS. On the left, we have users and applications issuing queries. Notice they do not touch the data storage directly. They must go through the DBMS. The DBMS consults the data dictionary to understand the structure and checks security permissions. Only then does it interact with the raw data storage. This security boundary is what allows us to enforce rules like referential integrity and access control centrally, rather than trusting every individual application to do it right. While most of us use SQL today, you will encounter legacy models, particularly in banking and insurance mainframes. First is the hierarchical model. Imagine an organizational chart, or a family tree. It uses a parent-child relationship. The rule is strict. A child can have only one parent. This is fast but rigid. If you want to model a situation where an employee reports to two managers, the hierarchical model struggles. To fix this, the network model was developed. It allows many-to-many relationships, where a record can have multiple parents, owners. However, it uses complex systems of pointers. If you break a pointer, you lose the data relationship. Navigating these databases requires knowing the physical path to the data, which makes ad hoc reporting very difficult compared to modern systems. On the left, we see the hierarchical tree. It flows strictly downwards. Employee 1 is owned solely by Department HR. To find Employee 1, you must start at Company and go through HR. On the right, the network mesh shows the flexibility improvement. Employee 4, highlighted in yellow, is linked to both Project A and Project B. This represents a many-to-many relationship, which is more realistic but technically more complex to maintain due to the pointers involved. The relational model revolutionized data management by separating data storage from data retrieval. We organize data into tables. Each row is technically called a tuple, and each column is an attribute. The magic lies in the keys. A primary key uniquely identifies a record like your social security number. A foreign key is a field that points to a primary key in another table. For example, an order table will have a customer ID foreign key that links back to the customer table. This allows us to join tables dynamically. Unlike the hierarchical model, we don't need to know the physical path. We just need to know the relationship. This flexibility is why RDBMS dominates the industry. This entity relationship diagram, ERD, visualizes the relational concept. We have a customer entity and an order entity. The line connecting them shows a one-to-many relationship. One customer can place multiple orders. Inside the order box, notice the customer ID field marked as FK, foreign key. This is the bridge that links the order back to the specific customer who placed it. This logical link maintains data integrity. A critical design process in RDBMS is normalization. This is the practice of breaking down tables to eliminate repeated data. For instance, instead of writing the customer's address on every single order they place, which wastes space and creates update errors, we store the address once in the customer table and just reference the customer ID in the order table. This prevents update anomalies. If the customer moves, we update one record, not thousands. We also enforce referential integrity. This rule says you cannot have an order for a customer that doesn't exist. The database will reject any attempt to create an orphan record. While normalization is great for integrity, be aware that overnormalization can slow down reporting, because the computer has to reassemble all those split tables. Here we see the flow of normalization. We start at the top with unnormalized data A, messy mix of order details and customer addresses. Through the normalization process, we split this into three clean, distinct tables: customers, products, and orders. The arrows at the bottom show how we reconstruct the information using ID links. We have moved from a chaotic, redundant state, red, to an efficient, structured state, green. How do we ensure money doesn't disappear during a bank transfer if the power fails? We use the acid test. These are the 4 pillars of reliable transaction processing. Atomicity means all or nothing. If I transfer money to you, 2 things happen: debit my account, credit yours. Atomicity ensures that if the credit fails, the debit is undone, rolled back. Consistency ensures the database rules are never broken. Isolation handles concurrency. If we both try to buy the last seat on a plane at the exact same millisecond, the system processes one and locks the other out. Durability means once the system says success, that data is written to non-volatile storage and will survive a crash. As auditors, we verify that the DBMS enforces these properties to prevent data corruption. This state diagram tracks a database transaction. It starts as active. If everything goes well, it moves to committing, and finally committed. This is where durability kicks in. However, if an error occurs at the active or committing stage, it moves to failed. Crucially, look at the path from failed to aborted. This represents the rollback the atomicity principle, ensuring the system returns to its clean starting state, leaving no half-finished data. Relational databases aren't perfect for everything. When we deal with complex engineering blueprints or multimedia, we use Object-Oriented DBMS, OODBMS. Here, the data and the code to manipulate it are stored together as an object, making it very efficient for complex data types. More recently, the rise of big data led to NoSQL. NoSQL handles massive amounts of unstructured data like social media posts or sensor logs that don't fit into neat tables. They use key value or document storage. However, a warning for auditors: NoSQL often trades strict consistency, ACID, for speed and scalability. This introduces new risks regarding data integrity that we must evaluate. This diagram contrasts the 3 types. On the left, relational table is rigid, with defined fields like name and age. In the center, object store contains not just data, image, but also methods, render, showing its utility for complex media. On the right, NoSQL document holds dynamic JSON blobs, illustrating its flexibility for unstructured big data. Each tool fits a specific job. Security and concurrency are paramount. Concurrency control manages thousands of users accessing the same data. We use locking to freeze a record while it's being updated so no one reads old data. However, this can lead to deadlock, where user A locks record 1 waiting for record 2, and user B locks record 2 waiting for record 1. The DBMS must detect and kill one process to resolve this. For security, we use database views. A view is a virtual table. If I want a clerk to see customer names but not credit card numbers, I create a view that excludes the credit card column. The clerk queries the view, not the raw table. This creates a powerful security layer. This sequence shows how a view protects data. The user asks for employee data. The view security layer intercepts this and queries the raw table, but specifically excludes the salary column. The raw table returns the data to the view, which passes the sanitized information to the user. The user never touches the raw table directly, ensuring confidentiality. We conclude with the human element, the database administrator, DBA. This is a high-privilege role. The DBA is the custodian of the data. They design the schema, tune performance, and most importantly, manage security and backups. Because the DBA has keys to the kingdom, segregation of duties is vital. A DBA should manage the structure, but should not be processing business transactions or editing production data. We also distinguish the DBA from the data administrator, DA. The DA defines the business names and rules. What is a customer? The DBA implements those rules technically, create table customer. Effective governance requires clear separation between these roles. This mind map summarizes the DBA's universe. The core branches are security, performance, availability, and architecture, the technical pillars. But look at the constraints branch. To maintain control, the DBA is restricted from production usage, processing transactions, and development access, writing code. This balance of power is essential for a secure IT operation.